Good evening, everyone. Nice to see you all here, waiting for my last presentation. I am Sai. I am from IMDEA Networks. Today, I am here to present my work, RISENSE. This is a joint work between IMDEA Networks and NEC Labs Europe. Imagine a scenario where base station needs to serve a user in a blind spot, that is someone behind the buildings like that. In this case, line of sight path is occluded by the buildings and the poor user in the blind spot experiences very low SNR. Is there a way to solve such a scenario? Yes, we could deploy one more micro base station close to the blind spot and users there will be happy. But then it is not energy efficient, also not optimal. Wouldn't it be wonderful if we can dynamically reshape the environment so that the poor users in the blind spot can experience better channel conditions? There is a way, I think you all know it. We could use Reconfigurable Intelligent Surfaces or RIS. For those who are not familiar with RIS is just a passive surface containing several antenna elements and phase shifters. So any signal impinging on the RIS can be redirected in some other direction so that users in that direction can be served. So like I said, RIS turns passive radio channels into programmable smart environments. This is very cost effective and energy efficient. So instead of deploying a micro base station, we could directly deploy a RIS, that is a passive RIS. So it is really energy efficient and the poor users who are in the blind spot can experience better signal conditions. This advantage of RIS is reflected in the multitude of research. I think you have seen in the past 10 years, there are many papers on RIS. We can do this, we can do that, new RIS designs. RIS then became meta surfaces. And now RIS is also able to support new applications, crazy applications. Hot topic of the hour, ISAC, physical layer security, etc. So, do you think RIS is ready to be deployed into current mobile networks? Sadly, answer is no. There is something still missing. So, what is that? Maybe most of you know already, and some of you really know because you met me yesterday. So, the control link, we go by example here again. Base station want to communicate to that UE there. So, it knows what phase shifter configuration to feed, but RIS doesn't know. So, RIS needs to be told which phase shifter configuration from the code book to pick so that the UE there gets optimal signal conditions. But then to tell, for base station to tell RIS, there is a need for a control channel, right? So in order to have that control channel, most of the literature, what they did, they assume either a wired control channel. So there is a wired link between base station and RIS, and whenever RIS want to, base station want to tell RIS to direct signal in which direction, it could use this wired link. Or we could use out-of-band devices like Bluetooth, LoRa. Sad part is none of these are part of any 3GPP standard. Furthermore, if you use these devices, you cannot integrate them with MAC and 5-layer procedures. Given this premise, I think you understood what is the problem we are tackling. What we are doing is, we are trying to provide a control channel while keeping RIS passive. So, what do you think are the challenges involved? First thing, RIS should have a receiving mechanism. Second thing, whatever the air interface we use, it should be 3GPP compliant. We can't change it. It is already fixed, OFDM. Dot. So, we need to use OFDM in a way so that we can tell RIS what to do. We need some efficient signaling protocol, and then RIS should be in synchronization with the base station. To address these challenges, we propose RISENSE. So RISENSE employs a hybrid RIS and a low power sensor. Then we have modified the air interface, but still we try to be compliant with the OFDM. Thus, we send some signal and tell RIS where to point the impinging signal. Let us start with the creation of receiving mechanism at the RIS. So this is how a regular RIS architecture looks like. So it's an array of unit cells. Each unit cell will have a radiating element and then a network of phase shifters, or which can be achieved by delay lines or varactor diodes. But then such a design, we cannot do anything much, we cannot receive anything. So in order to provide this receiving capability, we modify such a RIS architecture. So what we do, we connect the unit cells. When we want to receive some signal, we coherently combine impinging signal from each unit cell so that we can receive the RF signal. So if we zoom into the unit cell, it looks something like this. It has a sensing branch and a beamforming branch. So now we have a hybrid RIS. In general, RIS always has a controller. So in our case, we have a hybrid RIS with a controller. So we have a mechanism to receive the RF signal. Now what is missing? We need some way to bring RF signal to baseband, right? So either we go, then if we have to do traditionally, we need an oscillator, down converter, and then ADC. All these devices are power hungry. So if we employ these, we again defeat the purpose of using RIS. It is no longer energy efficient. We can throw that RIS, we can bring one more micro base station and put. It doesn't make any difference. So what we do, instead of, in order to avoid these devices, we employ a low power envelope detector. I'll tell you why in a minute. For now, please bear with me. We have a low power envelope detector. Now we go with the second challenge, air interface design. So the air interface must be compatible with 5G NR. Like I said, OFDM, nothing to do. So it should be easy to demodulate. Then we need to provide some fault tolerance. Finally, we need to be energy efficient. So if you see here, this is how a OFDM transmitter chain looks like. So why we employed envelope detector is, if you see, this is how you can write a OFDM mathematically. So what we do, if we send a OFDM signal, we need a complete RF chain. Instead, what we do, we embed the information on the pass band, that is on the envelope of the OFDM signal. So indirectly, what we are trying to do is, we are mimicking OOK with OFDM. So the missing link here is we need to find IQ samples, SI and SQ, in a way such that our passband signal has information embedded on top of the envelope. We have an algorithm, very simple one, which is we just need to solve a least square solution problem. We only need to solve it once and save it, reuse it whenever we need. Please refer to the paper to see how we do it. Like I said, it is a very simple least squares problem. Now we move on to the protocol design. Sorry. We have air interface, we have receiving mechanism. We want to do a better protocol design. So RIS, it cannot always look towards base station and think that base station is going to tell me something, right? So what we do, we divide the signaling into two phases, beacon and then the control message. Beacon tells RIS, hey, there is a control message coming in, please be ready. And then once RIS receives this thing, it will be aware that there is something coming in, I have to receive it, and based on that, I need to load the configuration. So like I said, we have two phases, beacon and a control message. During beacon, we do not use all the RIS elements, we only use few RIS elements. The number few depends on how far your base station and RIS is. And during the control phase, we use all the elements. Okay? I will explain this a bit better with an example. So consider there is a base station. So in the next TTI, it want to serve a user via RIS. So it scheduled that user X. So like I showed here, base station schedule user X here. Now what it has to do, it has to tell RIS there is an incoming configuration you need to change. So it will send a beacon. Sorry. Once beacon is sent, after a point of time, it will send the configuration. Once RIS receives the configuration, it has pre-designed code book. Based on the configuration, it will go to the code book, pick that configuration, load the RIS with all the phase shifter configuration. Now, when the data comes in, RIS is ready to redirect the signal towards the user. So this is how the complete signaling scheme looks like. There is a predefined beacon, then there is some time. We left that time so that RIS can change the phase shifters. And then there is a message which tells what are the phase shifters. Now I'll explain what happens during the beaconing phase at both base station and RIS. So like I said, at the base station, you have predefined sequence. You convert them into OOK within OFDM and then transmit them. So that signal looks like this. If you can see it properly, not properly, but then you can see the envelope. So say for example, the upper part is like 1 and the lower part is like 0. It's kind of embedding, 1, 0, 1, 0, okay? So RIS receives the signal, or hybrid RIS. Received signal, envelope is tracked by envelope detector. Controller samples the signal, and this is the sample signal from our sample signal which we captured. Now at the RIS, what it does after this, we have a neural network. One question you can ask me is why you want to say, you are saying that you want to keep RIS passive, but here you are putting a neural network. It doesn't make sense. Maybe you can ask it later. So this neural network, we use it to distinguish whether a beacon is detected or not. Okay? Once beacon is detected, RIS moves on to full sensing mode. Like I said, all the RIS elements will be active and it will look for a configuration. So during the control message phase, what happens at the base station? So for example, base station want to tell RIS load configuration 32. It already has computed subcarrier entries to make the configuration look like OK. That it transmits, RIS receives, again the story same, ADC samples, that is how the signal looks like. Now, how do I process this signal? This complete signal is divided into different number of bins, and each bin I just accumulate the energy and make a hard decision whether it's a 0 or 1. As simple as that. So the controller which already RIS is equipped with can do it. Then for error detection and correction, I think I forgot to mention there, we employ a simple convolutional encoder. Here we do the convolutional decoding. So we do error detection and correction. So we have bits are then converted into, bits are then encoded, then we add CRC, we send it, and here we do the reverse process. So once we decode, we have the configuration 32, we load the phase shifter configuration into the RIS, and now when base station transmits something, it can be redirected into that direction. And the last challenge is synchronization. So we assume that initial synchronization is done using a wire. After that, so there is a clock inside a microcontroller. We can use the ticks of the clock to compute the time. So all the intervals are fixed. We just have to count the ticks to be in sync. But as you know, controller drifts. So for that purpose, we rely on neural network again. So say for example, beacon is like this. Neural network detects YYY, you see in the bottom. Those things are saying that there is a beacon. And then once beacon is ended and noise starts, it will say neural network detects that it is noise. So this transition we can use for fine synchronization. So for evaluation, our setup is very simple. We are limited by the base station which we have. We have only one single antenna. So we built a RIS here. Architect of the RIS is here, Marco, you can talk to him later. We connect the RIS to an envelope detector and then to a controller. So to evaluate, first thing we want to evaluate beacons, how good neural network is able to detect and differentiate between beacon and noise. So as you can see, at low SNRs, neural network doesn't work fine. So from this, what we can see that we need at least 0 dB to detect beacon, to differentiate beacon and noise with 100% accuracy. Second thing, like I said, during beacon phase, we just want to use few elements to detect whether a beacon is incoming or not. So what is the link between the distance and the number of elements we use? So say for example, if we have a 10 by 10 RIS, we need almost all elements to detect the beacon so that we could provide 0 dB SNR. So key takeaway, like I said, for beacon to work, we need at least 0 dB. And then for number of elements, it is directly proportional to the distance between base station and the RIS. So in order to evaluate how good we are able to decode the control message, we did this experiment. Here we see, so maximum number of bits we could send, maximum number of bits we could send is 16, and minimum required SNR for that is 10 dB. So we are a bit limited. So if your phase shifter configuration is like you have a code book of 128, so you could use 7 bits to encode that information. Then if you have a half rate convolution encoder, you make it 16 bits and 2 bits for CRC. So you could use 16 bits. And yeah, so we measured our beam pattern in an anechoic chamber of the designed RIS. It looks something like this. You could see that beam is not so nice. That's because of the 3-bit phase shifter configuration we have. Because of that, you could see that beam is a bit skewed. To evaluate at a network level, what we did, we fall back to simulations here. We have a RIS and base station separated with some distance, and in the blind spot, we put many users. So for scheduling, we used a simple round-robin radio scheduling scheme, and we schedule the users for T slots. So it's a very stupid mechanism just to check how it works. So we see that we compare our RISENSE with no RIS, static RIS, and the state-of-the-art schemes like RS and MobiSys. RS and MobiSys are schemes which provide RIS reconfigurability at a second level, but we can do it at a symbol level. So you could see that in all the cases we are performing better, and when your scheduling interval is too large, RS and MobiSys, they are similar to our performance. And no RIS case, static RIS case, there is no scheduling involved, so they always perform constantly. Now, like I said, power consumption is the main thing we were banking on. If you see, there is no free lunch here. Since we put a active envelope detector, we do consume some power, that is 370 microwatts. But thing is, based on the size of the RIS, we could have a very large range, and then best thing is we could integrate into 5G NR directly. So now, like I started with, are we there yet? Now I want to finish with, are we there now? I would say no, but we are one step closer. All we need is a killer application. So if we have killer application, then maybe people will look more towards it. To conclude, we have an in-band, low power, real-time control interface for RIS. We do all this while keeping RIS passive and compliant with 5GNR. Thank you.
Cool. Let's thank our speaker. Questions? I'm going to ask the question you promised us. You're using neural network on several places. So
Yes.
In the power consumption, have you actually considered the compute power consumption
Yes.
for running? Okay.
Yes.
So can you tell us a little bit on how you can achieve that?
First I'll tell why neural network. So most of you know that, in order to detect beacon, either you need to correlate, right? You need to correlate. If you see a peak, you say beacon is there. But then envelope detector, all the signal you receive is positive. So even if you correlate, it's like weighted sum, it always shoots up. So you cannot use in this case. So for that reason, we went back to neural networks, okay? And then your second question, power consumption. Okay, so our neural network is very, very simple. So it's 32 times 10 neural network. It's a very simple multiplication. We did implement it on microcontroller, and we put the power consumption results in the paper. You could check. It is minimum.
So it runs on an MCU?
Yes. We used STM microcontroller, so it has some help to implement neural network, so we used that. Yeah.
Okay, cool. Yeah, go ahead.
Thanks for your presentation.
Yeah.
I'm Jida from Stanford University, and I'm very curious, how does the RIS talk back to the base station? Because
No, RIS doesn't talk back. It's one-way communication.
okay, so how do you form the feedback loop? Like, how does the base station know that, oh, the configuration I sent to you is actually successfully decoded?
Yeah, I think we just take it for granted that it was a successful transmission. So during the deployment phase, we need to be careful in choosing the parameters, because it's one-time thing. You can put RIS in a way that it is close or it is far away from RIS, far away from base station. But only thing you need to guarantee is it gets minimum required SNR so that the transmission is successful. So it's all deployment. It's all based on deployment.
Okay, thank you.
Thank you.
Let's thank our speaker once again. This wraps the last session of today. And